Hi everybody, welcome to the General Chemistry Review for the Introduction to Organic Chemistry. And so we're going to start by looking at electron configurations. And so you do have to be able to read your periodic table in this fashion, starting from 1s and all the way through the periodic table. So using a periodic table, you might notice that when we are talking specifically about an abbreviated format, called the noble gas abbreviation, that in this case, Ne would be incorrectly written, and it should be instead written as, I'm going to make sure I'm writing, this should instead be written as He. And so that means that we would be right here in this location, and that would tell us that what we have is actually some carbon. Okay, so you do have to be able to write it correctly, as I just demonstrated, but you also have to be able to read what element it is. That should be easy peasy stuff. So let's go ahead and move ourselves along to the next part here. Okay, so what is the shorthand electron configuration for phosphorus? And when you go look up phosphorus, you note that phosphorus is actually sitting right here on your periodic table, so that you know automatically that you are going to end up with 3p3. But you need the other parts here to be able to show it correctly. So in brackets, you need to show the noble gas, and then you need to show it as 3s2 3p3. And then what about sulfur? Sulfur would be easy if you've already done phosphorus. Then you would be able to say, well, sulfur is right here next to it, so we would simply write this as Ne3s2 3p4. And being able to count it all out and remember things is going to be important. Now, one of the things that you need to pay attention to are our two exceptions. And our two exceptions are going to be in the chromium and in the copper that you have to pay attention to. So please keep in mind, when we are talking about chromium and copper, they both steal an electron from the S into the P. So for chromium, we are going to have, if we just did it normal and it was not an exception, then our shorthand configuration for it would be AR for S2 3, and I don't know why it's not allowing me to write 3D4. But because we know that it steals, we end up with AR for S1 3D5, correctly written for chromium. Now, what about for copper? Copper is the same sort of thing. We would steal the one electron from the S, so we end up with AR for S1 and 3D10. So there's that, just a little bit of reminder of the things that are going on there. That also means that if we have a charged particle of chromium, let's say we have chromium 3 plus, that's a really weird 3. Let's say we have chromium 3 plus. Let's remember that then that means the electrons come from the outer energy level first and work inside. So our electron configuration for chromium 3 plus is going to come out to AR. The 4s1 electron is going to disappear, and 2 of the 3D electrons are going to disappear. So we'd end up with 3D3 for chromium 3 plus. What about if we have copper 1 plus and copper 2 plus? Well, copper 1 plus does exactly what you expect, and that looks funny. Let me erase that real quick and rewrite it. Copper 1 plus does exactly what you would expect. It takes the 1 electron from the 4s, so you end up with AR 3D10, that's copper 1 plus, and copper 2 plus leaves us with AR. 4s1 disappears, and one of the 3Ds disappear, so we end up with 3D9 for our electron configurations for the ions. Okay, so we are going to hurry up and go on here to our next part as a review. What are valence electrons? Well, let's remind everybody that we can define valence electrons as electrons in the outermost energy level. And those are the ones that we remove first in an ion situation. What is the difference between valence electrons and the total valence of an atom? I think those are pretty much the same thing. The total valence of an atom might sometimes be defined as all of the electrons that are outermost electrons, not including the very first energy level. I really don't like using that terminology, so we're just going to refer to valence electrons. Okay, so what about chemical bonding? We need to be able to talk a little bit about what drives chemical bonding. Chemical bonding, basically, it is energy that drives chemical bonding. And it is the question that we're trying to ask is, does the compound formed exist with less potential energy? Okay, the more potential energy you have, the greater the chance that you are going to have more of an unstable compound. So the more stable a compound is, the less potential energy it has. So let's talk about ionic bonding in general. Go all the way back to sophomore year. Ionic bonding is the transfer of electrons from metals to nonmetals. Okay, so what about covalent bonding? It is the sharing of electrons between nonmetals. So already you are hearing terminology and things that you just need to be able to remember and use. So for instance, here comes the Octet Rule. Basically, it is the completion of an energy level or valence shell with 8 electrons. Okay. So as we've said already, bonding lowers the potential energy for a compound, and the strength of the bond determines the properties of the bond. In other words, the compound. If we have a compound with a large amount of strength amongst bonds, it's going to take a lot of energy to break that compound, and then so you're going to have a lot of energy stored in those bonds, and it's going to take a lot of energy to break those bonds. Okay, let's go ahead and move on to our next part here. So here is a good example of what we see in the case of hydrogen, the hydrogen molecule, H2. The reason why you see hydrogen exist in nature as H2 is because it really does have a lower energy when it is bonded together than when the atoms are separate from each other. So for that reason, it is far more stable and exists in nature as a molecule, a diatomic molecule, instead of as separate atoms just floating around in the air. So let's go ahead and move on here. So let's make sure that we understand that bond lengths are pretty much additive with a little bit of wiggle room for overlap. So let's take into account the carbon to hydrogen bond, which, as you can see from this, is carbon has an atomic radii of 0.77 angstroms. That is angstroms right there. And we're going to bond it with some hydrogen. So that comes out to 0.30 angstroms. And when you add those together, you're going to estimate that the total bond length would be 1.07 angstroms. When you go look at it in real life, it's a little bit longer. And this comes out to electron repulsions is what you are going to have that come out to. And almost everything, when you see bonding happens, you also have to take into account electron repulsions. When there are more electron repulsions. Simple to think about it that way. All right, let's scroll up. Okay, so here we have bond length in and when we are comparing bond lengths and why do they increase? Why does a bond length increase from carbon to nitrogen to carbon to carbon to carbon to phosphorus? Simply put, it has to do with the sizes of the atomic radii. When we have smaller atomic radii, you're going to have a smaller bond length. A larger atomic radii, greater bond length. Pretty easy to wrap your head around that kind of information. So bond energy and bond breaking and bond formation. This is a cornerstone for IB, so let's make sure we got this. Bond formation is going to be an exothermic process. Bond forming releases energy to form stable bonds. Okay, so remember that was the reaching of the lower potential energy. Bond breaking, however, has to be endothermic because energy must be absorbed to break bonds. And we got to break the bonds first before we make new bonds. So energy must be absorbed. Otherwise, the bonds are just going to stay there. Remember that we made stable bonds. Stable bonds means that they're unlikely to just spontaneously fall apart by themselves. So energy must be absorbed to break bonds. And let's keep in mind that the shorter the bond length, the greater the energy it's going to take to break a bond. That means that we're going to have a lot of attraction between particles amongst the electrons from electrons of one atom to electrons of another atom, especially if those bonds are very, very short. So to be able to break those bonds, short bonds means it takes more energy to break the bonds. Longer bonds means it takes less energy to break the bonds. So let's go ahead and take a look at our table here so we can see what that looks like. So as you can see, multiple bonds, the greater the number of bonds, this looks like bond lengths here. Bond lengths are getting smaller and smaller and smaller with the greater number of bonds. But then we compare that to bond strength. Let's go ahead and make sure we have this down. This is one of those tested things that IB loves to test about. The shorter the bond, the greater the bond energy. In other words, the energy it takes to break the bond. So a triple bond will take a lot of energy to break the bond, whereas a double bond or a single bond will take less energy. And a smaller bond, like between a carbon to a nitrogen, will take more energy to break than between, say, a carbon to an oxygen. So things to keep in mind. So this is a very important one to make sure you have in your notes. Okay, so then what is electron negativity? Remember, electron negativity is the tendency of an atom to have an uneven bond with another atom. In other words, to pull electrons closer to itself. The larger the number, the more chance that it's likely to pull electrons closer to itself. So you'll notice the one that is more likely to have electrons pull closer to itself is fluorine, and then some of the other ones like potassium is very low and sodium is very low. So you're going to have fluorine be the most electron negative element on the periodic table. You're also going to notice that there are no noble gases listed on this periodic table. And remember, that's because noble gases have full energy levels and are highly unlikely to react by attracting electrons to themselves. So not all covalent bonds are created equal. That means some and the majority of covalent bonds are considered polar covalent bonds. So the greater the difference in electron negativity, then the greater the chance that you have a polar covalent. Okay, so the greater the difference. So that means we're going to have a highly polar bond with pretty much anything and fluorine, highly polar bonds. So if we had to just look at the periodic table, and sometimes that's all you get is a periodic table with no values on it, and you have to be able to determine which one is the most polar bond. Anything as compared to fluorine is going to be the most polar bond. Sometimes you won't be given that, and then you're looking for the two atoms that are the farthest from each other, as in from the left side of the periodic table and the right side of the periodic table. So for instance, a carbon to fluorine bond is going to be more polar than a carbon to oxygen bond, just looking at the differences in electron negativity. But let's say you don't have fluorine. So then you would look at the hydrogen to carbon bond difference, which comes out to, as you can see, 0.4, as compared to, say, carbon to nitrogen, which is 0.5. And so you'd have to be able to say, well, carbon to hydrogen is going to actually be, if you have the numbers, you can calculate it, but if not, you might have to make an educated guess that the farther the elements are apart from each other, the greater their difference in electron negativity. All right, so we are going to, and you'll see the little chart there of what does, how do we know when it's polar covalent, and so on. Let's go ahead and take a look at identifying which things are polar covalent bonds. Remember, anytime a bond is between the same two elements, it's completely nonpolar. Anytime a bond is between two elements that are different, it's going to have a polar electron negativity difference, but we are going to have to be able to represent the formatting of the how does this look. And I want you to be able to see that we have electron negativity differences, and let me make sure I do that right. So we are always going to be pointing the arrow towards the more electron negative element. So it doesn't really matter which direction you point the arrow. It is going to instead matter that you recognize that there are going to be inequalities of the atom. And if there is not a equal but opposite arrow, then you are going to be able to expect to say, well, these all cancel each other out, cancel, 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 leaving us one polar arrow. So that makes this a polar bond. So we can go through and take a look at all of these. If these two cancel and these two cancel and these two cancel, then here is our polar bond. Same thing happens again, cancel, 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 leaving us, okay, so now we've got two polar bonds going here. So more polarity in this one. And so do you notice that I am not actually looking at any electron negativity values? I'm just looking for places where there's going to be an expected difference in electron negativity. So again, cancel, 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 but then I end up with this, and you would have to be able to say, well, this is going to be a polar molecule. I just don't know how much. But you can see that there will be differences. So again, cancel, 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 cancel. I can say those two cancel. I'm probably going to guess these two cancel and these two cancel. And then that leaves me here nothing but same elements all bonded to each other. So I have found a non-polar molecule. And so the same thing again, cancel, 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 same, cancel, cancel, cancel. So there is my one polar. So you see I've circled the polar areas of each of these. Okay, so the question comes down to, why do we care if a molecule is polar or nonpolar? So here we have two examples of a polar and a nonpolar molecule. And the answer is it has to do with how does it behave in a chemical reaction. Both of these would be considered very stable molecules. They both have reached their lowest potential energy. So it's not having to do with potential energy so much, but because of the uneven distribution of electrons, in these molecules. So for instance, the electrons in hydrogen are located directly in the middle here, and whereas the electrons in this bond are here, we have a bunch more of electrons around this one. I'm counting to make sure I did that right. I think I might have to erase one of my electrons. There we go. We also have all of these other electrons on the inner energy levels of the chlorine. So we have a large amount of electrons sitting here, and this leads us to a very covalently polar bond. While it is sharing electrons, it is highly polar, so this reactivity is much, much higher. And it's, as you know, HCl is a strong acid. HCl is highly reactive. HCl responds with highly reactive and forceful reactions. So it's going to change how it behaves based on its type of bond it has. Okay. Okay, so one of the things that we use is an electron density map, which is basically looking at the areas of electron density. So the red is going to indicate high areas of electron density, and I specifically want to focus you onto this molecule right here. This is a highly tested one. On carbonate, why does the electron density show that the hottest part is in between each of the bonds? So let's remind you, on a carbonate ion, we actually have let's count up valence electrons. So here's our valence, and you're going to want to draw the carbonate ion into your note. So I have 4 valence electrons for the carbon, plus I have 3 times 6 valence electrons for each oxygen, plus I have 2 extra electrons for that charge. So I have 18 plus 2 is 20 plus 4. I have 24 electrons. 24 electrons I have to show in my bonding. And so I'm going to end up with carbon in the center, and I'm going to go ahead and set up my 3 oxygens around it. And I've used a total of 6 electrons right now. And then I would go ahead and bond or show the rest of my electrons around here. And when I do that, I find out really quickly that I've used up all my electrons and my carbon does not have a full octet. So one of the oxygens, and we don't know which one because they're all equal to each other, is going to periodically be sharing its extra electrons into a double bond. Except you can see that the electron density in this picture is the same in all cases. So what that means is that we have pictorial evidence of the presence of a resonating structure. And let's remind you that you must show the dashed lines for the other bonds. You must show this in a bracket, and you must show the -2 charge on the outside of it to be able to show your resonating structure. So that means yes, as part of your review, you are going to have to be able to draw Lewis structures, and you're going to have to be able to do resonance structures as well. But you'll notice that we have a special way to draw this out. So we want to be able to, which direction is the electron density flowing? So in this case, we would be able to identify that our electron density is actually here, and we have electron density going here, and we have electron density here, which you might have been able to guess already leads you to understanding or maybe being able to characterize this as, while those are polar bonds, the overall ion molecule is actually a nonpolar molecule. Okay, moving ourselves along here. Okay, let's try some, and we've done this a little bit already, and so I'm going to skip this part, showing all polar bonds in the direction of electron density. Just being able to show this, usually this is not something that is tested, but you need to be able to say where the electron density. Okay, so let's remind everybody that we had some things that canceled out. So cancel, 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 cancel. So we have an area of polarity right in here. And we always draw the arrow so it points from the less electron negative to the more electron negative. So that's why I drew my arrow from the hydrogen to the nitrogen. Again, cancel, 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 cancel. And these two are really close to each other. So I'm just gonna guess that that's the case, but that might be the wrong case. I'd have to actually look that one up. And then here, cancel, 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 cancel. So I'm going to have this that goes here and this that goes here. So overall, I have a polarity. So this one is by far the more polar of the parts. Okay, so now we're going to move ourselves along. And let's answer this question. What is so special about carbon? So what's special about carbon is that it has 4 valence. And that means that it can bond in 4 different locations. Bond, let's write that 4 times. Okay, so that means carbon is very versatile in how it can bond. It can double bond, or it can triple bond. Okay, so carbon is very, very versatile. All right, and so we're going to be focusing the rest of our learning, of course, on what is bonded around the carbon. And you might already be able to identify that a lot of hydrogens are bonded around the carbon. There's some oxygens and there's some fluorines and what have you, but there are a lot of hydrogens bonded around the carbon. Okay, so here is going to be your assignment for today. Let's remind you that drawing Lewis structures, we're going to want to depict or draw Lewis structures based on their number of valence electrons. We're going to follow the octet rule. We're going to remember hydrogen can only have 2 electrons around it. And then before we go on, I'm going to make sure that you understand how to draw different types of formulas. But let's make sure that you understand you are going to need to draw the Lewis structure for each of these. And I'm going to go ahead and get you started with with hydrogen peroxide. So let's take a look at a hydrogen peroxide, and this is going to be done on your own paper, and then you are going to be uploading what you have. So I'm going to go demonstrate for you not only how are we drawing these, but the counting of valence electrons, the identification of the geometric as well as the electrical shapes of the molecules, and being able to identify whether it's polar or non-polar. Trying to think of all the things, but let's go ahead and get into it. So we have some hydrogen peroxide, H2O2. So the first thing I'm going to do is I'm going to count up my valence electrons. And so I'm going to have 2 times 1 for the hydrogen and 2 times 6 for the oxygen. So I'm going to end up with a total of 14 valence electrons. Okay, so I'm going to go ahead and put the 2 oxygens side by side here with each other, and I'm going to go ahead and bond, thinking of symmetry, bonding each hydrogen on either side. And so as you can see, I've only used a total of 6 electrons so far, with each bond being representative of 2 electrons. So then I can go ahead and add in the extra electrons here. So now I've used up a total of 2, 4, 6, 8, 10, 12, 14 electrons, and I have a completed octet in all cases, including the small octet for the hydrogen. And I can go ahead and say that this appears to be nonpolar, with all of my bonds canceling each other out, or which are between 2 of the same atoms. I can say that this appears to be a linear type of molecule with, I would have to call that an AB2 format. And we would have to be able to also say that as far as electrical geometry, we'd have to be able to say, okay, around a specific element. So electrical geometry, let's just say, what is the electrical geometry around each oxygen? And so I would be able to remember, you look at the numbers of electrons. And so I have 4 bonding locations, including lone pairs. So electrical geometry is going to be the tetrahedral format. Now, if we also had to be able to say what is the hybridization around each oxygen, we would have to call each oxygen's hybridization sp3. If we were doing it around each hydrogen, we would call that just a plain old sp. Right now, so the things that you need to have listed here are valence electrons. You need to have the Lewis structure. You need to say whether it is polar or nonpolar. You need to say what its structural geometry is. You also need to say what its electrical geometry is, and you need to say what its hybridization is. So for each one of these, you can expect there to be a value of 1, 2, 3, 4, 5, 6 points for each one, and you have a total of, I'm just trying to count here, 10, 11, 12, 13. So a total of 13 times 6. So that does not add up to 100, but you need to know that is how you're going to be graded on this. And this is going to be a file for you to upload. All right. Thank you, everybody. Bye-bye.